Um, so yeah, I don't actually want to do a whole lot today. We'll just prove one theorem, I think. I was writing my solutions last night for homework 4. Have you guys done homework 4 yet? In any case, number 1, if you haven't, the question that I think asks you to show that the incidence axioms are implied by the SMSG axiom. So it's an incidence. So neutral geometry at least is an incidence geometry. I had to invoke postulates I think 5 and 7 to show that points actually existed. So when we were going through them in class 5 through 8, they deal with planes and 3-dimensional space. So we didn't really talk about them because we're not ever going to use them. But for this homework problem, you do need 5 and 7. So just flip to the back page in the book. It gives you all the SMSG axioms, and yeah. So it's a big hint. But anyway. All right, because somewhere you have to establish that points actually exist, and the existence of points is actually hidden in those later postulates. So we only have one last thing to do. We were talking about congruence conditions, and we have to talk about SSS. But before we do side, it's going to follow almost immediately from this hinge theorem or hinge lemma, if you don't want to distinguish it with the name of a theorem. And it says quite a lot, but I'm gonna sort of explain what this says a little bit better, I think, once you've written it down. So if two sides of one triangle are congruent to two sides of a second triangle, and the included angle of the first triangle is larger in measure than the included angle of the second triangle. So there's all of our hypotheses. Then the length or measure of the third side of the first triangle is larger than the third side of the second triangle. Third side of the first triangle is larger than the length of the third side of the second triangle. haven't drawn a particularly compelling case. How about we hinge this a little bit bigger? All right, so this is how this is posed. And I don't really want you to think about the way this is posed as it is, but this is the way it's posed. It says if I have two different triangles, but they have two pairs of congruent sides, so here AB is congruent to DE, AC is congruent to DF. If they have two pairs of congruent sides, but the included angle in one is bigger than the included angle in the other, so here this guy is obviously the bigger angle, then the opposite side is going to be longer than the opposite side of the shorter angle. So this is sort of strictly what this is saying. But I don't think that's really the right way to think about this, right? This is saying more than this. This is saying that think about just having a single triangle, right? This is why this is called the hinge theorem. Think about just having a single triangle. What this is saying is that if I just have this hinge here, this sort of just this hinge, as I increase this angle, the length over there is getting longer, right? In other words, the length of this side is a monotonically increasing function of just this angle. So you plug in that angle, you get out the length. This angle determines that length because these two sides are fixed. But and not only that, it's not just a function of this angle, it's monotonically increasing. As I increase that angle, this length increases. All right, so this is the hinge theorem. How are we going to prove this? The idea is let's try and take a copy of this triangle, the second triangle, and we're going to build a copy inside of it. Okay? And then we're going to invoke somehow the triangle inequality to show that this side must be shorter than this side. So this is how we're going to prove this. We're going to build the first thing we're going to do is just build a copy of the second triangle inside the first one. And once we've built that, then we have to be a little bit clever as to how we get this triangle inequality to work for us. But here's our proof. So let triangle ABC and triangle DEF be such that our hypotheses are satisfied. So be such that side AB is congruent to side DE, and side AC is congruent to excuse me, DF, and the measure of angle BAC is greater than the measure of angle DDF. So this is just the picture we had before those two triangles. Again, I'm going to do what I suggested, and then I'll draw a picture of what's going on. But we're building a copy of the smaller triangle inside the bigger one. So since the measure of angle BAC is greater than the measure of angle EDF, there exists a point that we'll call R in the interior of angle BAC such that angle BAR is congruent or equal in measure to angle EDF. And furthermore, let's let P be a point on this ray, on the point on the ray AR, so that triangle ABP is congruent to triangle DF. Okay, so maybe I'm never going to work with this triangle DEF again, but let's just throw it up here so we can indicate what things are congruent. But we have these two triangles, right? We started off with these two triangles and we said, okay, AB is congruent to DE, AC is congruent to DF, and the measure of angle BAC, this angle right here, is bigger than this one. Okay, so since this angle is bigger, I can find some point in the interior of this angle so that when I construct the ray, that ray is the same as this angle right here, or the angle created. So let's just say I take this as what I call the point R. Here's my point R. And that gives me this ray. And in particular, I've built this ray or chosen this point R so that this angle BA, did I call it BAR? BAR is congruent to EDF. Okay, so that was the first thing we did. The first thing we did was we chose a point R. We know there's a point R in the interior of this angle, so that we construct this smaller angle on the inside. And then I want to come into this ray. I want to come to this ray AR that's extended infinitely. I'm not going to draw the rest of it because it's going to clutter the picture. But I'm going to extend this ray to a point P. To a point P. So that these two triangles, ABP and DEF, are congruent. What does that mean? That means I've chosen P along this ray so that this side is the same length as this side. And moreover, I guess that means, if you want to indicate it, that means that side, that third side, is congruent to that third side. So as promised, that was the first thing we were going to do, is build a copy of this triangle inside the other one. The picture doesn't have to look like this, by the way. P might be outside somewhere, it's okay. But roughly this is what's going on. So now I want to somehow show that this side must be shorter than this side. Right? That's the end goal here. That's the conclusion of the hinge theorem, is show that this side is shorter than this side. How do I do that? Well, I could finish this picture. I could draw in a triangle here, And I could use the triangle inequality to say that the sum of these two sides is bigger than this one, or maybe this one plus this one is bigger than this one. But the problem is I don't know anything about the length of this side, right? So I have to be a bit more clever than this. I can't just build in the triangle as it stands. What we're going to do is something quite a bit more clever. So here goes. Let S be a point so that the ray AS bisects angle CAP, and let Q be its point of intersection with side CB. And let Q be the point of intersection. Of this ray with side BC. Don't really need R anymore, but we'll keep it on there. All right, so what I'm doing is I'm coming into, I said CAP, right? We're coming into this angle, and we're bisecting it. So I'm just drawing in the bisector of this thing. Maybe S is somewhere way out there. We'll keep it out there so it doesn't clutter the picture. And Q is the point where it meets the side. There's Q. All right, so these angles here are the same because of construction, right? We've drawn in the angle bisector. And it turns out this is what I want. I want this triangle. Okay, so by SAS, we have the two triangles in this picture are congruent to each other. They don't look like it at all because my picture's horrible, but there are two congruent triangles in this picture. This side is the same length as this side. Obviously this side is the same length as that side because it's the same side, and these two angles are equal. So this triangle here and this triangle here, those are congruent by SAS. Alright, so by SAS we have the triangle, let's call it ACQ. I'm going to go ACQ. ACQ is congruent to triangle APQ, thank you. APQ. And in particular, what I really want from that is the fact that this means this side PQ is the same length as this side CQ. So PQ is the same length as CQ. And I think we have it now. I think we can finish this. All we have to do is invoke the triangle inequality. Finally, by the triangle inequality, remember what we want to do, right? We want to show BC is longer than BP. Well, what I can do is I can invoke the triangle inequality on this last triangle here. I can say that BQ plus, so this side plus this side is longer than this one. So BQ plus QP is longer in measure than BP. Right, this is triangle inequality from last side. It says the sum of any two sides of one triangle is longer than the third side. So all I'm doing is invoking triangle inequality on this one right here. But we already showed I can do a substitution now. QP, I called it PQ already, but same thing. QP is the same as QC. So PQ plus CQ, or QC, is longer than BP. And obviously, BQ plus QC is the original side of ABC. It's the side BC. So I think I can fit one more line in here. BC is bigger than BP. But what was BP? BP was constructed so that BP is exactly the same as EF. Right? This is just a copy of the smaller triangle. So BC is bigger than EF. Done. So again, the way you should think about this is don't think about this in terms of comparing two different triangles, right? Think about this in terms of just having a single hinge, right? Just this picture, just have this hinge, and as you increase the angle here, the distance between these 2 points gets further apart. This is all it's saying. A nice proof, because we're really not doing a whole lot. Again, we just sort of took the smaller one, built a copy on the inside, and then realized we have to be a little bit more clever to get our triangle inequality to work for us by bisecting this angle. But it's fairly sleek, I think. Any questions? Okay. I said this was the only proof we were going to write today. We still have SSS to talk about, but we're not going to prove it. So, SSS follows immediately from the hinge lemma, basically. If the vertices of two triangles are in one-to-one correspondence, so we've got a bijection between them that preserves the vertices. Such that all three sides are congruent. Respectively to all three sides of the other triangle. To all three sides of the other triangle, then they are congruent as triangles. In other words, if you know all three side lengths of a triangle, that triangle is uniquely determined. Again, nice to keep in mind that you already know this fact, this is a Euclidean fact, but it's true also in this more general neutral geometry with no parallel postulates. Meaning it's true in, it'll be true in hyperbolic geometry for us as well. Again, I'm not writing a proof. We can sketch one really quickly. I've got two triangles that satisfy SSS. What did the hinge theorem tell us? Hinge theorem told us that this side length here is a function of this angle, right? Well, if they both have the same side lengths, opposite this angle, then they both must have the same angle here. Because this side length is an increasing function of this angle. So those two angles must be congruent by the hinge theorem. And now there's nothing left to do, right? Now I can invoke SAS. So the triangles are congruent by SAS. So not much to do here. The hinge theorem does it all for us. Does that make sense without writing down all the details? Awesome.
Just one clarification, but that's only true because we know all three sides.
Exactly. If you
Because you could.
you need two sides to invoke the hinge theorem, and
Oh,
now
right.
because I know the third sides are equal.
Right.
Yeah. Yeah.
Gotcha.
So last thing, let's just state one more quick theorem. Again, without proof, but it's one more congruence condition, this time on quadrilaterals. And it's one we talked about in Geometry 1, I think. It's SASAS. SASAS. Will we ever use this in the class? We actually might, so worth stating. If the vertices of two convex quadrilaterals. So getting away from triangles here. Two convex quadrilaterals are in one-to-one correspondence such that three sides and the two included interior angles of one quadrilateral are congruent to the corresponding parts of the second one, to the corresponding parts of a second quadrilateral, then the quadrilaterals are congruent. Okay, so what is this saying? This is saying I'll draw them so that they're actually look congruent, because they will be. I've got these convex quadrilaterals. And I know, what do I know? Three sides, so let's call them three sides. 1, 2, 3 matches up there. three sides are congruent, and the two included interior angles. So this angle matches up with this one, this angle matches up with this one. Then the claim is that that's enough knowledge. That's all I need to know to automatically conclude that the fourth sides must be the same length, and these other two angles must be congruent as well. Why does this follow? Again, I'm not going to write down a proof, but I believe we can just take what we know about triangles. Let's see if we can sketch this out. If I slice this into two triangles. My hope is that by slicing this into two triangles, we'll have enough knowledge. Can I conclude that their diagonals are the same length? Yeah, right, by SAS. SAS tells me that these two triangles are the same, so those diagonals, I guess we'll put 4 little marks on there, those diagonals must be the same length. Because these two triangles are congruent, I know that that angle there matches that angle there. And the bigger angles were already known to be congruent, so just by subtracting off the orange part, I can conclude that this angle is congruent to that angle. And now we have enough. Now I have SAS again telling me that I don't have enough marks, but telling me that that side is the same length as that side, and all of these angles match up. So again, without writing down the details, that would sort of be how you would proceed with cutting into triangles first. Which gives us 15 minutes. And there's one thing I've sort of regretted not talking about, because I wanted to show examples of this a couple of times already. So let's go all the way back to 2.7. Hyperbolic geometry. And I want to give you a model. All right, we'll talk a lot more later on about why this model works, all of the details, but a model for hyperbolic geometry. There are 3 very, very common models that people use. 3 very, very common models, all have their pros and cons. I'll give you the simplest one right now. This is the upper half plane model. Very, very closely related to the Poincaré disk model. Sometimes people call this the Poincaré upper half plane model, but I'll just call it the upper half plane model. And the points are going to be all points x, y, with y bigger than 0. Okay, so in other words, what points are those? Those are everything above the x-axis, right? Not including the x-axis, so it's the open half plane, the open upper half plane. So I'll dash it out because we're not actually going to include it. And my lines are going to come in 2 different types. One is just vertical lines. So in the upper half plane model, here is an example of a line. Any vertical line. Those are the simple ones. But what you should do is you should think of this as being a circle of infinite radius. So the rest are also going to be circles. These are actually semicircles centered on the x-axis, on this boundary. So here, for example, is another line. Here, for example, is another line. How about I draw one more? How about I draw one more? Here's another line. Okay. We have lots of lines drawn. And here already in this picture, you can see a couple of things going on. Right? I don't want to write this, but for example, what I've sketched here, how many sides does that shape have? 3, right? So this guy, that's a hyperbolic triangle. It's kind of small. I could have drawn it a bit bigger, but that is a hyperbolic triangle. And throughout this class, when I draw examples of hyperbolic triangles, I'm typically going to draw them something like this, with these curvilinear edges, because in hyperbolic models, your edges are sort of parts of these Euclidean semicircles, right? So this is why I'm going to draw my triangles looking like this. What else can you see? How about, here's a line. Here's a point not on the line. And you can already see I have 2 lines passing through this point, right? I've got this one and this one. I have 2 lines passing through this point that are parallel to this one. Why are they parallel? Because they don't ever intersect it. So again, we're already violating the Euclidean parallel postulate. I have a line, a point not on the line, and I have more than one line passing through it that's parallel. And of course, there's not just these 2 lines, right? I can draw all sorts of families of circles passing through this thing that are going to be parallel and never intersect this. So there's actually infinitely many. The boundary here, the x-axis, what's happening at the boundary? This is actually, the boundary is playing the role of infinity. So the nice thing about this model is, okay. The nice thing about this model is the angles you see, the angles you measure, the Euclidean angles that you see, are actually the angles in hyperbolic geometry. But the distances obviously are not, right? If I want this point, or if I want this to be playing the role of infinity, right? So if I'm walking along this line, to the infinity, I should never get there, right? But if I measure this distance in Euclidean sense, what's that, like 10 inches? So if I'm going to talk about distances in this model of hyperbolic geometry, I need my distances to stretch out. As I walk along here, I need these distances that are close to the boundary to represent very, very, very large distances. So we're not going to get into the details of that, into the underlying metric of this model right now, but I want you to be familiar with a particular model, what lines look like, and so on. And this is all it is. So lines are semicircles that are centered on the boundary, or if you think of very, very, very large semicircles, well, stretch their radius out to infinity, and you just get the limiting case, the vertical lines. Okay, we'll stop here. Again, the exam's on Friday. If you have any questions, feel free to email me, otherwise, I'll see you in here for a 50-minute exam.